Forget the Hollywood dogfight and the lone ace with a scarf trailing in the wind. The reality of 21st century aerial combat is a far colder, more brutal affair, and its latest protagonist is the Shenyang J-16. This is a machine born from the pitiless logic of physics and the silent flicker of electrons, a world where victory is measured in microseconds and decided by fractional advantages in sensor range. Every composite panel on its airframe is a calculation of survivability. Every line of its code a bet on who lives and who dies. To understand the J-16 is to understand the trajectory of Chinese air power itself, from a dependent pupil to a self-sufficient and increasingly assertive peer. This aircraft is not simply a product of reverse engineering. It is the capstone project of a decades-long national endeavor to master the complex, systemic art of designing, integrating, and mass-producing a top-tier combat system, a strategic achievement that arguably outweighs the performance of any single airframe. Be sure to subscribe to the channel so you don't miss new analytical reviews. The story of the J-16 is inextricably linked to the saga of the Sinoflanker, a long and often contentious relationship with the exceptional Sukhoi Su-27 airframe. The genesis lies in the 1990s, a period of strategic recalibration for the People's Liberation Army Air Force, PLAIF. Recognizing the profound technological gap exposed by Western air power in the First Gulf War, Beijing turned to Moscow. In 1992, China purchased its first batch of Su-27 air superiority fighters, and by 1996, it had secured a landmark $2.5 billion deal to license-produce 200 of them at the Shenyang Aircraft Corporation under the designation J-11. This was intended to be a straightforward technology transfer, a way to rapidly modernize the PLAF's backbone. However, the arrangement began to fray after the assembly of the first 95 kits. Around 2002, China unveiled mock-ups of the J-11B, a variant that was conspicuously absent from the licensing agreement. This new aircraft, which began appearing in prototype form by 2006, was an unauthorized derivative, a product of what might charitably be called the School of Creative Procurement. While retaining the flanker's superb aerodynamic shell, the J-11B was a declaration of technological independence, incorporating indigenously produced avionics, a glass cockpit, and, crucially, Chinese-made weapon systems. This move, while causing a significant diplomatic and industrial headache for Russia, was a pivotal step. It marked the point at which China was no longer content to simply assemble foreign designs, but was determined to master, modify, and ultimately surpass them. Concurrently, the PLAF had also acquired the two-seat, multi-role Sukhoi Su-30 strike fighter in 1999, a heavier, more versatile platform comparable to the American F-15E Strike Eagle. The Su-30 provided the doctrinal and technical template for a long-range strike fighter, complete with a strengthened airframe, a more robust undercarriage to handle greater takeoff weights, and an in-flight refueling probe for extended missions. The J-16, which is believed to have made its first flight around 2011-2012, is the synthesis of these two evolutionary paths. It is not a direct copy of the Su-30 but rather a hybrid, a conceptual fusion. Shenyang engineers took the airframe of the twin-seat J-11BS, itself the two-seat trainer version of the indigenous J-11B, and integrated the structural and mission system lessons learned from the Su-30 all while populating it with a new generation of purely Chinese technology. The result is a machine with a Russian soul but a distinctly Chinese mind and nervous system, a platform that leverages a proven world-class airframe as a vessel for a suite of electronics and weaponry that has left its progenitors far behind. The Shenyang J-16 presents a formidable silhouette, an unmistakable descendant of the flanker lineage. With a length of 21.9 meters, a wingspan of 14.7 meters, and a height of 6.36 meters, it is a large, heavy fighter, built for range and payload. Its aerodynamic design retains the classic features that gave the original Su-27 its legendary maneuverability: a large strake, wing-body blended configuration that generates immense lift and allows for stable flight at high angles of attack. However, beneath this familiar shape lies a structure that has been fundamentally re-engineered. One of the most significant departures from its Russian-built ancestors is the extensive use of composite materials throughout the airframe. This application of advanced materials, including carbon fiber composites, results in a substantial weight reduction compared to the all-metal construction of the Su-30MKK, improving the aircraft's thrust-to-weight ratio and overall performance. The empty weight is reported to be approximately 17,700 kilograms, allowing for a maximum takeoff weight of a staggering 35,000 kilograms. Further enhancing its survivability, the J-16 is coated in a distinctive, low-visibility, silver-gray paint that is not merely for camouflage. This coating contains radar-absorbent materials, RAM, designed to reduce the aircraft's radar cross-section, RCS, particularly against higher-frequency fire control radars, making it a more difficult target to detect and track. While this does not make the J-16 a true stealth aircraft, it represents a pragmatic approach to signature reduction that aligns with its doctrinal role. At the heart of the machine, providing the raw power for its Mach 2 performance, are two Shenyang WS-10 Taihang afterburning turbofan engines. The story of the WS-10 is a microcosm of China's entire aerospace industry, a long, arduous, and monumentally expensive struggle for self-sufficiency. Initiated in the 1980s to create a domestic equivalent to the Russian Saturn AL-31, the program was plagued for decades by profound technical challenges. Early production models were notoriously unreliable, with reports of service lives as low as 30 hours between overhauls, compared to the AL-31's already modest 400–500 hours. The engines suffered from inconsistent quality control, issues with meeting thrust targets, and a particular Achilles heel in the metallurgy of their single-crystal turbine blades, the critical components that must endure temperatures exceeding 1600 C while spinning at thousands of RPM. For years, the engine seemed to possess a temperament actively hostile to the concept of sustained flight, with the PLA logging nearly 20,000 faults in its first 3 years of service. Yet, through sheer persistence and immense national investment, these issues were gradually overcome. The current WS-10B variant powering the J-16 is a mature and reliable power plant, reportedly generating around 135 kN of thrust with afterburner and boasting a thrust-to-weight ratio approaching 9.1. The successful maturation of the Taihang engine, allowing it to become the standard power plant for China's premier fighters, represents a strategic victory of the highest order, finally severing the umbilical cord to Russian engine suppliers and ensuring the J-16 program can proceed at a pace dictated solely by China's own industrial capacity. This evolution reflects a philosophical divergence from its Russian cousins. Where a platform like the Su-35 prioritizes extreme kinematic performance through advanced engines with three-dimensional thrust vectoring, the J-16's development has focused on achieving solid, reliable performance while channeling primary investment into the digital domain of sensors and networks. A clear bet that future battles will be won by the side that masters the kill chain, not just the dogfight. If the airframe is the J-16's body, its avionics suite is its digital soul, and it is here that the aircraft makes its most decisive break from its Russian ancestry. The centerpiece of this advanced electronic architecture is an indigenous active electronically scanned array, AESA radar, housed within a light-colored radome that is a telltale sign of its advanced nature, along with the absence of the traditional nose-mounted pitot tube seen on older flanker variants. This system represents a generational leap over the mechanically scanned PSA radars found on even advanced Russian fighters like the Su-27. The J-16's AESA is reported to have a detection range of 200–250 kilometers against a typical fighter-sized target and the ability to simultaneously track between 15 and 20 targets. The inherent advantages of AESA technology are profound. The beam can be steered electronically almost instantaneously, allowing for interleave search, track, and engagement modes. It is highly resistant to electronic jamming, and it can operate in low probability of intercept, LPI modes that make it difficult for an enemy's electronic support measures to detect its emissions. This powerful sensor is complemented by an offset infrared search and track (IRST) system located just forward of the cockpit, providing a passive means of detecting and tracking targets via their heat signatures at ranges of up to 80 kilometers. This dual sensor approach allows the J-16 to hunt for targets without revealing its own position by emitting radar energy. Inside the tandem cockpit, the analog dials and cluttered instruments of older Soviet-era designs have been completely swept away. The crew operates within a modern glass cockpit, dominated by large, full-color multifunction displays, MFDs, that present fused tactical information in an intuitive format. Both the pilot and the weapons systems officer, WSO, are equipped with a helmet-mounted display, HMD, which projects critical flight and targeting data directly onto their visors, enabling high off-bore sight missile engagements and dramatically enhancing situational awareness. However, the true power of the J-16's digital suite lies in its network-centric design. The aircraft is equipped with high-capacity secure data links that allow it to seamlessly integrate into a wider system of systems. It can receive and share targeting data in real time with other assets, most notably airborne early warning and control, AEW&C aircraft like the KJ-500. This capability enables sensor fusion on a grand scale, where data from the J-16's own radar and IRST is combined with information from off-board platforms to create a single, comprehensive, and God's-eye view of the battle space. This architecture transforms the J-16 from a mere fighter into a highly effective node in a distributed network. Moreover, the PLAF is pioneering a doctrinal evolution for this two-seat platform. Instead of the WSO serving a traditional role focused purely on weapons employment, as in the F-15E, Chinese military thinkers are developing a new concept for the backseater as an Air Mission Commanding Officer, AMCO. In this capacity, the second crew member leverages the aircraft's powerful sensors and connectivity to manage a complex battle space, directing formations of other friendly aircraft, coordinating with ground and naval units, and potentially controlling unmanned loyal wingman drones. This innovative use of the second crew member to mitigate the information overload of modern warfare and act as a forward battle manager positions the J-16 as a crucial test bed for the PLAF's future air combat concepts, including those envisioned for the two-seat J-20S stealth fighter. A fighter is ultimately defined by its claws, and the Shenyang J-16 carries a formidable and multi-domain arsenal. With a reported maximum weapons payload of at least 8 tons and 12 external hardpoints, it is a versatile and heavily armed platform capable of executing a wide array of missions. In the air-to-air arena, the J-16's armament reflects a clear emphasis on beyond visual range, BVR combat, and engaging targets from extreme distances. Its primary long-range weapon is the PL-15 missile, a munition that has garnered significant attention from Western military analysts. The PL-15 is equipped with an advanced AESA seeker for superior tracking and countermeasure resistance, and it is powered by a dual-pulse rocket motor. This innovative propulsion system allows the missile to coast for a significant portion of its flight before reigniting its motor in the terminal phase, providing a massive energy boost to defeat maneuvering targets at its maximum range, which is estimated to be between 200 and 300 kilometers. This capability significantly outranges the standard AIM-120 AMRAAM variants used by most Western air forces. For even longer-range engagements against high-value assets like tankers and AWACS aircraft, the J-16 can carry the massive PL-17, a very long-range missile with a potential reach exceeding 400 kilometers. For engagements within visual range, the J-16 employs the PL-10, a highly agile short-range infrared homing missile capable of high off-bore sight shots in conjunction with the pilot's helmet-mounted display. The aircraft's air-to-ground and maritime strike capabilities are equally robust, transforming it into a potent standoff strike platform. It can carry a wide variety of precision-guided munitions, including laser-guided bombs like the LS-500J and satellite-guided glide bombs. A key standoff weapon is the KD-88 air-to-surface missile, a turbojet-powered weapon with a range of approximately 200 kilometers. It is guided by a television or imaging infrared seeker, allowing the WSO to manually guide the missile to its target in the terminal phase via a data link. This man-in-the-loop capability makes it highly effective against moving or well-camouflaged targets. In the anti-shipping role, the J-16 is arguably one of the most dangerous platforms in the world, primarily due to its ability to carry the YJ-12 supersonic anti-ship cruise missile. The YJ-12 is a ramjet-powered sea skimmer that can travel at speeds between Mach 2 and Mach 4, covering its 400-500 kilometer range in minutes and presenting an exceptionally difficult target for shipboard defense systems. The J-16 can also carry the more conventional YJ-83K, a subsonic but still effective anti-ship missile. For close-in strafing, the J-16 retains the powerful Gryazev-Shipunov GSH-31 30mm cannon inherited from its flanker ancestors. This comprehensive and long-range arsenal is not merely a collection of disparate weapons, it is a carefully curated toolkit designed to execute China's anti-access area denial (A2AD) strategy. By fielding weapons that can hold adversary assets at risk from hundreds of kilometers away, the J-16 serves as a key instrument for creating a lethal bubble, making it prohibitively dangerous for opposing naval and air forces to operate anywhere near China's periphery. In the crowded sky of 4.5 generation fighters, the J-16 does not exist in a vacuum. Its capabilities must be measured against its global peers, each representing a different philosophy of air combat design. Its most direct analog is the American F-15E Strike Eagle and its latest iteration, the F-15EX Eagle II. Both are large, twin-engine, two-seat aircraft designed for multi-role dominance. The F-15EX likely holds an edge in its more mature and powerful AN/APG-82 AESA radar, its staggering ordnance flexibility, and superior range and endurance, particularly when fitted with conformal fuel tanks. However, the J-16 counters with a potentially larger radar aperture owing to the flanker's wider nose section and an air-to-air missile suite, particularly the PL-15 and PL-17, that boasts a significant range advantage over the F-15 standard AIM-120. Furthermore, the PLAF's doctrinal exploration of the Air Mission Commanding Officer role for the backseater represents a more forward-thinking approach to crew utilization in a data-saturated environment compared to the USAF's more traditional weapons systems officer concept for the F-15E. The comparison with its Russian cousin, the Su-35, is a study in family rivalry and divergent evolution. The Su-35 is arguably the king of kinematics, a pure air superiority fighter whose combination of powerful AL-41F1S engines and three-dimensional thrust vectoring nozzles grants it unparalleled agility in a visual range dogfight. The J-16, lacking thrust vectoring, cannot match this supermaneuverability. However, the contest shifts decisively in the J-16's favor in the BVR arena. Its ESA radar is a full generation ahead of the Su-35's Urbis E-PISA radar, and its indigenous avionics, data links, and weapons are more seamlessly integrated and generally more advanced. Indeed, reports from within the PLAF itself suggest a degree of disappointment with the Su-35's electronic systems, viewing them as outdated compared to domestic offerings. Against the U.S. Navy's workhorse, the F/A-18E/F Super Hornet, the J-16 leverages the fundamental advantages of its land-based heavy fighter design. The J-16 boasts a higher top speed, greater service ceiling, and significantly longer combat radius than the Super Hornet, which is inherently compromised by the structural requirements of carrier operations. While the Super Hornet is a rugged and versatile platform, and its EA-18G Growler variant sets the global standard for airborne electronic attack. In a direct comparison of multi-role performance, the J-16's superior range and kinematics give it a distinct advantage. Ultimately, the J-16 occupies a unique niche. It synthesizes the most desirable traits of its competitors, blending the large airframe, heavy payload, and impressive fuel fraction of the Eastern heavy fighter philosophy with the advanced ESA sensor suite, network-centric architecture, and sophisticated munitions of the Western approach. It may not be the absolute best in any single category. It is not as agile as the Su-35 or as versatile a bomb truck as the F-15EX. But its lack of any glaring weaknesses and its high performance across all key metrics make it a uniquely well-rounded and formidable adversary. The proliferation of advanced, networked integrated air defense systems, IADS, has rendered the electromagnetic spectrum a primary battleground. Dominance in this invisible domain is no longer a luxury but a prerequisite for survival, let alone victory. It is this reality that drove the development of the Shenyang J-16D, a dedicated electronic warfare, EW variant, and China's direct answer to the U.S. Navy's formidable EA-18G Growler. The J-16D is a specialized instrument, physically and electronically reconfigured for the singular purpose of fighting and winning the war for the spectrum. The modifications from the baseline J-16 are substantial and telling. The most obvious changes are the removal of the internal 30mm GSH-30 Mark I cannon and the nose-mounted infrared search and track IRST system. This sacrifice of kinetic and passive detection capabilities frees up critical internal volume and power generation for a comprehensive integrated electronic warfare suite. The aircraft's nose radome is reshaped, likely housing a specialized ESA radar optimized for electronic attack functions in addition to traditional radar modes. The airframe is studded with an array of new antennas and dielectric fairings, and most prominently, it features large, permanent electronic support measure, ESM pods on its wingtips, which are analogous to the AN/ALQ-218 pods on the Growler, and are used to detect, identify, and geolocate enemy emitters with high precision. The J-16D's offensive punch comes from a suite of powerful jamming pods carried on its underwing and fuselage hardpoints. At least 3 distinct types of pods have been observed, suggesting a sophisticated multi-band approach to jamming that allows the aircraft to target a wide range of radar systems, from low-frequency early warning radars to high-frequency fire control and missile guidance radars. This modular pod system, combined with its internal EW suite, likely gives the J-16D the ability to engage multiple emitters simultaneously across a broad frequency spectrum, conduct both brute force barrage jamming and more subtle deception jamming, and potentially even execute non-kinetic cyber attacks against networked air defense systems. While its primary role is soft-kill electronic attack, the J-16D retains a potent hard-kill capability for suppression and destruction of enemy air defenses, SAD-dead missions. It can carry a variety of anti-radiation missiles, arms, such as the YJ-91, a derivative of the Russian Kh-31P, which are designed to home in on and destroy enemy radar transmitters. The operational doctrine for the J-16D mirrors that of its American counterpart. It is designed to act as a force multiplier, escorting strike packages of conventional fighters like the J-16 and even stealth aircraft like the J-20 into heavily defended airspace. By blinding and disrupting the enemy's IADs, the J-16D creates temporary corridors of electronic silence, allowing friendly forces to penetrate defenses and strike their targets with a much higher probability of survival. The very existence of such a sophisticated and expensive platform is a clear signal of the PLAF's strategic intent. It demonstrates a mature understanding that any future high-intensity conflict, particularly a scenario involving Taiwan, will be fought against a technologically advanced adversary in a contested electromagnetic environment. The J-16D is not a defensive asset. It is a key enabler for offensive air operations and a linchpin in China's strategy to dismantle an opponent's ability to fight back. An aircraft's true measure is found not on a spec sheet, but in the turbulent air of real-world operations. While the J-16 has yet to see combat, its operational history is being written daily in the contested airspace of the Indo-Pacific. It has become the PLAF's platform of choice for asserting Beijing's expansive territorial claims, serving as the primary instrument for patrols and intercepts in the South China Sea and the Taiwan Strait. These encounters are far from routine. They are often aggressive, high-stakes displays of brinkmanship. In May 2022, a J-16 intercepted a Royal Australian Air Force P-8 Poseidon surveillance aircraft over the South China Sea, flying dangerously close before releasing a cloud of chaff and flares, some of which were ingested by the P-8's engines in a flagrantly unsafe maneuver. A year later, in May 2023, a J-16 performed a maneuver colloquially known as thumping on a U.S. Air Force RC-135 rivet joint, cutting directly in front of the reconnaissance plane's nose and forcing it to fly through its turbulent jet wash. These incidents, while condemned as unprofessional, serve multiple purposes. They are a form of coercive diplomacy, a physical harassment of intelligence-gathering assets, and, most critically, a valuable opportunity for live training. Each intercept allows PLAF pilots to practice detecting, tracking, and maneuvering against real adversary aircraft, testing the limits of their machines and their own nerve while gathering invaluable data on Western operational patterns. Perhaps the most telling episode in the J-16's short history is the widely publicized claim by PLAF pilot Li Pengfei. According to a broadcast on China Central Television, during a 2024 coastal exercise, Li's J-16 encountered 2 foreign stealth fighters. He claimed to have performed an aggressive barrel roll and inverted flight within 10 to 15 meters of one of the aircraft before achieving a simultaneous radar lock on both, forcing them to retreat. From a purely technical standpoint, the claim is plausible under specific, narrow conditions. The effectiveness of stealth is not absolute. It is dependent on aspect, range, and the frequency of the illuminating radar. At extremely close, within visual range distances, any fighter's radar has a chance of achieving a lock, and the J-16's IRST could also have been a factor. However, the true significance of this event lies not in its technical veracity, but in its masterful execution as strategic communication. The carefully managed release of the story serves as a powerful piece of psychological warfare. It is designed to puncture the myth of the invisibility cloak surrounding fifth-generation aircraft, sowing doubt among adversary pilots and planners about their assumed technological overmatch. It sends a clear message that China believes it has developed the means, whether through technology, tactics, or sheer pilot aggression, to counter America's most advanced assets. For domestic audiences, it is a potent morale booster, showcasing the prowess of Chinese pilots and homegrown technology, with pilots like Wang Songxi describing the J-16 in state media as flawless and superior to any aircraft they had previously flown. The J-16's operational record, therefore, is one of carefully calculated aggression, a blend of physical intimidation and sophisticated narrative warfare that makes it a far more significant strategic tool than a simple patrol aircraft. The J-16 platform, as it exists today, is not an end state, but a foundation for future evolution. Its development will be guided by the overarching modernization goals of the People's Liberation Army, which has laid out an ambitious roadmap to achieve a fully modernized military by 2035 and a world-class force by 2049. A key milestone on this path is the year 2027, the centennial of the PLA's founding, which has been set as a target for accelerating the integrated development of mechanization, informatization, and intelligentization. This concept of intelligentized warfare envisions the deep integration of artificial intelligence, machine learning, and advanced networking into every facet of military operations, from command and control to individual weapon systems. The J-16, with its modern open architecture avionics, ample power generation, and large airframe, is an ideal testbed for these futuristic concepts. Near-term modernization will likely focus on incremental but significant hardware upgrades. The integration of more advanced and efficient variants of the WS-10 engine, such as the WS-10C, which already powers later batches of the J-20, would further improve the J-16's performance, increasing thrust and fuel efficiency. Continuous software updates to its radar and sensor fusion algorithms will enhance its detection and tracking capabilities, while the integration of new and longer-range munitions will keep its arsenal at the cutting edge. However, the most transformative modernization path lies in the realm of artificial intelligence. Reports have emerged of a J-16 variant unofficially dubbed Zhisheng, or Intelligence Victory, that is being used to test an AI co-pilot in the back seat. In this configuration, the AI would act as a tireless, hyper-efficient WSO, capable of managing the complex sensor suite, identifying and prioritizing threats, executing electronic warfare functions, and processing vast amounts of data far faster than a human operator could. The two-seat layout of the J-16 is critical for this developmental work, as it allows a human pilot to supervise, evaluate, and interact with the AI in a real-world flight environment, providing the essential human-on-the-loop oversight needed to build trust and refine the algorithms. This AI co-pilot could eventually be tasked with controlling a swarm of unmanned, loyal wingman drones, effectively turning the J-16 into a flying command and control hub for a team of autonomous systems. The J-16 is thus serving as the crucial bridge between the PLAF of today and the human-machine teamed force of tomorrow, the platform where the abstract theories of intelligentized warfare are being forged into practical operational reality. The Shenyang J-16 is not a revolutionary aircraft. It does not push the boundaries of aerodynamics or propulsion in the way a truly novel design might. Instead, its significance lies in its masterful and pragmatic evolution, a perfect encapsulation of China's technological prowess and strategic ambition in the early 21st century. It represents the culmination of a decades-long process of absorbing, digesting, and ultimately improving upon foreign technology. By marrying a proven world-class airframe with a suite of cutting-edge, entirely indigenous electronics and weapons, China has created the quintessential 4.5 generation multi-role fighter. It is a machine that combines the endurance and payload of the Eastern Heavy Fighter School with the sensor dominance and network centricity of the Western approach, resulting in a formidable platform with no obvious weaknesses. In its standard configuration, it is a long-range interceptor and a potent strike aircraft. In its J-16D variant, it is a specialized tool for dominating the electromagnetic spectrum. In all its forms, it is the instrument of choice for projecting power and enforcing China's will across the contested waters of the Indo-Pacific. But perhaps the J-16's most profound significance lies in its sheer numbers. With production rates high and a fleet size already estimated to be approaching 500 airframes, and with the potential to grow to over 800, the J-16 represents the crucial element of mass in the modern air power equation. While potential adversaries may field more technologically exquisite fifth-generation platforms, they do so in smaller, more precious numbers. The J-16 provides the PLAF with a vast and highly capable force that can control territory, attrite an opponent through sheer volume, and present a credible, sustainable threat across multiple fronts. It is more than just a fighter. It is the reliable steel backbone of a rising air power, the versatile and powerful workhorse upon which China's more ambitious fifth and sixth generation aspirations will be built.